Welcome back. A few episodes ago, we ran Gaussian elimination. Clear a system down to upper triangular form by subtracting multiples of one row from another, then back substitute. Today we notice something we walked right past. Every one of those row operations is itself a matrix. The whole elimination is one big product of matrices. And if we keep the receipt instead of throwing it away, a clean and powerful fact emerges. The matrix A factors as a lower triangular matrix L times an upper triangular matrix U. We write that A equals L times U. The lower factor L stores the multipliers we used. The upper factor U is the result of the elimination, holding the pivots. Once we have L and U, solving a system splits into two easy triangular solves, and we can reuse the factorization across as many right-hand sides as we like. We finish with pivoting, which keeps the whole method working when a pivot is 0 or uncomfortably small. Start with a single move that drives elimination, subtract m times one row from a row below it. Remarkably, that move is a matrix. Take the identity matrix and place a single extra entry, -m, in the row and column of the operation. Call it E. When you multiply E times A, the result is A with exactly that row operation performed. The matrix carries out the bookkeeping for you. Now here's the feature that makes everything work. To undo this operation, you simply add the multiple back instead of subtracting it, so the inverse of E is the same matrix with a sign of that one entry flipped from -m to +m. Nothing else changes. This is special to subtract a multiple operations. Their inverses are trivial, and the multipliers sit there in plain sight. That simplicity is what lets us assemble the lower factor L almost for free. Now collect the steps. Elimination keeps multiplying A on the left by elementary matrices until what remains is upper triangular. Call that result U. So a product of elementary matrices times A equals U. To isolate A, move the elementary matrices to the other side by inverting them, and remember each inverse only flips one sign. The product of all those inverses is the lower factor, and we call it L, so A equals L times U. Two small miracles make this clean. First, the product of those lower triangular inverses is itself lower triangular, with ones all along the diagonal. Second, and even better, you do not have to multiply anything out. The below diagonal entries of L are exactly the multipliers you already used during elimination, the M21, M31, M32, and so on. So as you eliminate, you fill U with the rows you produce and L with the multipliers you subtract. The factorization is the elimination simply recorded. Here is how the factorization pays off when you solve a system. You want to solve AX equals B, and you know A equals L times U. Substitute to get L times the quantity U times X equals B. Now give the inner part a name, let Y equal U times X. The single hard problem has become two easy ones. Stage 1, solve Ly equals B. Because L is lower triangular with ones on the diagonal, you read off Y1 immediately, then Y2, then Y3, marching from the top down. That is forward substitution. Stage 2, solve Ux equals Y. Because U is upper triangular, you read off the last unknown first, then the one above it, marching from the bottom up. That is back substitution. Each stage is just a sweep through a triangular matrix with no elimination required. Two cheap triangular solves do the job that a full elimination used to do. Let me make the efficiency concrete. Factoring an n by n matrix into L times U costs on the order of 1/3 n cubed operations. That is the expensive part, but you do it only once. Each triangular solve afterward costs only about n² operations, much cheaper because there is no elimination, just a single sweep. Now picture the common situation where the matrix A stays fixed, but the right-hand side keeps changing. The same circuit driven by many inputs, the same structure loaded many ways. If you ran full elimination every time, you would pay that 1/3 n cubed over and over. Instead, you factor A once, then handle each new right-hand side with one forward solve and one back solve, roughly 2n² each. The cubic cost is paid a single time and amortized across every solve. This is exactly why serious software stores the factors L and U, rather than computing the inverse of A. The factored form is the efficient way to solve again and again. Let's look at the shapes. On the left is the full matrix A, every entry filled in. It equals the product of two triangular matrices. The first factor, L, is lower triangular. Its whole upper right region is 0. It carries one straight down the diagonal, and below that diagonal sit the multipliers from elimination, the ones highlighted in gold. The second factor, U, is upper triangular. Its whole lower left region is 0, and along its diagonal sit the pivots, again highlighted. So a fully populated matrix on the left is built from two matrices that are each half empty. That emptiness is the entire point. Because the zeros are guaranteed, you never have to work through them, and solving against either factor becomes a single clean sweep. Picture L as the record of what elimination did, and U as the triangular system elimination produced. Together they reconstruct A, and apart they make solving easy. Let's watch the two-stage solve as a flow. At the top is the chain of reasoning. Ax equals b becomes L times the quantity u times x equals b, and naming u times x as y splits it into solve Ly equals b, then solve ux equals y. On the left sits the lower triangular factor L with a green arrow pointing down its diagonal. That is forward substitution. You find y1 at the top first, then y2, then y3, sweeping downward, each value using the ones already found above it. The middle arrow carries the intermediate vector y across to the right. There sits the upper triangular factor u with an orange arrow pointing up its diagonal. That is back substitution. You find the last unknown x3 at the bottom first, then x2, then x1, sweeping upward. Two single direction passes, one down and one up. No elimination, no fractions piling up. Just read the triangle in the right direction and the unknowns fall out one at a time. A natural question: does every matrix factor at L times U? Not quite, and it is worth knowing when it does. The plane factorization, with no row swaps, exists as long as elimination never runs into a zero pivot. There is a precise way to say this. Every leading block in the top left corner must be invertible, but the practical version is simply, if the pivots come out non-zero, you get a clean L times U. To make the answer unique rather than one of many, we pin ones along the diagonal of L. That is the standard Doolittle convention, and with it the factors L and U are determined completely. When a pivot does come out zero, or just dangerously small, a row swap becomes necessary, and then we factor P times A as L times U instead. That swapped version always exists for any square matrix whatsoever, so the takeaway is A equals L times U for the well-behaved case, and P times A equals L times U in full generality. Let's factor a real matrix. Take A with first row 2, 1, 1, second row 4, 3, 3, third row 8, 7, 9. Eliminate the first column using the pivot 2 in the top left corner. The second row begins with 4, which is 2 times the pivot, so subtract 2 times the first row from the second. The multiplier m21 is 2. The third row begins with 8, which is 4 times the pivot, so subtract 4 times the first row from the third. The multiplier m31 is 4. After that, the first column below the pivot is cleared, and the bottom right block has become 1, 1 in the second row, and 3, 5 in the third. Now eliminate the second column with pivot 1, the third row has a 3 there, so subtract 3 times the second row. The multiplier m32 is 3. What remains is U, upper triangular with diagonal 2, 1, 2. The lower factor L has 1s on its diagonal, and the multipliers 2, 4, 3 placed exactly where they were used. Multiply L times U, and you recover A. The factorization checks out. Now solve a system using the factors we just built. Take the right-hand side, b equal to 4, 11, 29. First, the forward stage, solve Ly equals b from the top down. The first equation gives y1 equals 4 directly. The second says y2 equals 11 minus 2 times 4, which is 3. The third says y3 equals 29 minus 4 times 4 minus 3 times 3, which is 29 minus 16 minus 9, or 4. So y is 4, 3, 4. Now the backstage, solve ux equals y from the bottom up. The last equation is 2 times x3 equals 4, so x3 is 2. The middle equation is x2 plus x3 equals 3, so x2 is 1. The top equation is 2x1 plus x2 plus x3 equals 4, which gives x1 equal to 1/2. The solution is 1/2, 1, 2. Notice we never re-eliminated anything, we just swept down through L and back up through U. Here is the case that breaks the plane factorization, and the fix in action. Try to factor the matrix with first row 0, 1, and second row 2, 3. The pivot in the top left corner is 0. We are stuck immediately. There is no multiplier that clears the entry below a 0 pivot, because you would have to divide by 0. So A equals L times U simply fails for this matrix. The remedy is a row swap, encoded by a permutation matrix P that exchanges the two rows. After multiplying, P times A has first row 2, 3, and second row 0, 1. But look, that matrix is already upper triangular. So no elimination is even needed. The lower factor L is just the identity. The upper factor U is P times A itself, and P times A equals L times U holds exactly. This tiny example shows the whole point of pivoting. A matrix that has no plane factorization gains a perfectly good one the moment we are allowed to reorder its rows. One thing can spoil the plane factorization, a pivot equal to 0, which you cannot divide by, or a pivot that is tiny, which is just as dangerous because dividing by a small number magnifies rounding error. The fix is simple and is what every serious solver does. Before clearing a column, look down it and swap in the row whose entry there is largest in size, so you always divide by a healthy pivot. A row swap is itself a matrix called the permutation matrix, written P. If you account for all the swaps up front, the clean statement of the factorization becomes P times A equals L times U. The permutation P simply records the order the rows ended up in. To solve AX equals B, multiply both sides by P to reorder the right-hand side, then run the same two triangular solves on L and U. With pivoting in place, every square matrix has a factorization of this form, and this is precisely what professional numerical software computes when you ask it to solve a system. Once you own the factorization, two more useful quantities come along almost for free, which is a good reason to compute L and U in the first place. First, the inverse of A. Remember that the columns of the inverse are just the solutions of AX equals each standard basis vector. Solve against the first basis vector to get the first column of the inverse, and so on. Since you already have L and U, each of those is one cheap pair of triangular solves, so the whole inverse costs n forward and back sweeps rather than n full eliminations. Second, the determinant. Because L has ones all down its diagonal, its determinant is 1, so the determinant of A is just the determinant of U, which for a triangular matrix is the product of its diagonal pivots. If you used pivoting, you also flip the sign once for each row swap, so the same L and U that solve systems will also invert the matrix and hand you its determinant. The factorization is really a multi-tool. A little history. The elimination at the heart of this method goes back to Carl Friedrich Gauss in the early 1800s, who used systematic row operations to fit astronomical data, decades before matrices were even standard notation. Through the 1800s and into the 1940s, mathematicians, including Jacobi and later Doolittle and Kraut, recast that elimination as the explicit factorization A equals L times U, and their names still label the particular schemes for laying out the multipliers and pivots. In 1948, Alan Turing, yes, that Turing, wrote a careful analysis of how rounding errors propagate through the factorization and argued for partial pivoting as the way to keep it numerically stable. Today, LU factorization with pivoting is the absolute workhorse of scientific computing. It is the routine quietly running inside LAPACK and essentially every numerical library, every time a computer solves a linear system. Let's recap. Every elimination step, subtracting a multiple of one row from a lower row, is a near identity matrix, and its inverse just flips the sign of that multiplier. Collecting the steps reveals the factorization A equals L times U, a lower triangular L carrying ones on its diagonal and the multipliers below, times an upper triangular U carrying the pivots. To solve AX equals B, you forward solve LY equals B from the top down, then back solve UX equals Y from the bottom up. Two cheap triangular sweeps. The big efficiency win is that you factor A only once, at cubic cost, and then reuse L and U for every new right-hand side at merely quadratic cost, which is why solvers store the factors instead of the inverse. And when a pivot is 0 or tiny, you swap rows to the largest available pivot and factor P times A as L times U for stability, exactly what real software does. Next episode, we read the pivots off U to decide when a system has one solution, infinitely many, or none. Today we discovered that Gaussian elimination was secretly a matrix factorization all along. Each elimination step, subtract a multiple of one row from a lower row, is multiplication by an elementary matrix, a near identity matrix with one extra entry. Multiply them all together and they reduce A to an upper triangular matrix U. The crucial trick is that the inverse of each step just flips the sign of that one multiplier, so collecting the inverses builds a lower triangular matrix L whose entries are exactly the multipliers you used with ones on the diagonal. The result is the factorization A equals L times U, a lower triangular L times an upper triangular U. With it, solving AX equals B splits into two easy stages. First solve LY equals B by forward substitution, top to bottom. Then solve UX equals Y by back substitution, bottom to top. Each triangular solve is cheap. And here is the payoff. If you must solve the same A against many different right-hand sides, you factor A once and reuse L and U every time, turning expensive work into nearly free work. When a pivot is 0 or dangerously small, you swap rows first, recorded by a permutation matrix P, and factor P times A as L times U instead. Next episode, we read pivots off U to decide exactly when a system has one solution, infinitely many or none. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.